Hi, welcome to day 4 of the video tutorial series, and in today's lecture I'd like to go through the way that we find the slope of an equation using differentiation versus traditional method, to share how easy or what the basic of differentiation is like while using the neural networks. So let's assume this to be a quadratic equation, which is 3x squared minus 4x plus 5. And if we just substitute x with some values, such as anywhere between minus 5 to 5, and plot it, we could see that at different x values, the function returns some numeric numbers. So if we like to assume this to be the properties of a neural network at different weights or at different x, we could see the loss that we are seeing that is present at different values of x. So in order to get closer to the weight or like closer to the loss or lowest loss, we could see that our x should have some value around 0 to 2. Now, since we are creating a neural network with some random weights, as I have shared in the previous lectures, let's assume that if you're starting at x is equals to 3, that is the weight at 3. This is just some random number that we got started with. And now there are two ways in which we can calculate the differentiation for this given function. One is the traditional method, where we substitute where we go through the differentiation of this function. So the differentiation of 3x squared minus 4x plus 5 is almost equals to 3 into x squared will become 2. So 3 into 2 into x minus 4. And when we substitute x as 3, then the answer will be 18 minus 4, that is 14. So 14 is the slope of the equation. This is the slope of the equation at x is equals to 3. Now, in the real world, we have billions of x, and writing this differentiation equation will not be possible in this traditional method. So to overcome that, we will try to find the slope of a point with a specific solid principle of differentiation or derivative. So if you look at Wikipedia, we can find out the slope by changing x or a with a very small value. So when we add a small value to the x, and we can know how the function is responding, and based on the output of this function's response, we can extrapolate the value of slope. So I've just implemented the same function over here. So for the same f of x, where x is at 3, we could see that the output is 20. So when x is 3, when we substitute the value here of x as 3, we get output of 20. And if we add x by a small margin, so now the x is 3.00001, and the function responded with this number. So in order to know, in order to differentiate, we need to know how much of a change did h have on this function. So this is the amount of change that h had on the function. And to standardize this, we need to look at, so we need to divide it by h, that is the h is changed by some factor, h is added to x, hence x is changed by some factor. In order to normalize this, we divide it by h, and we could see that the value is closer to 14. So this concludes that we can find the slope of any point uh, in this differentiation by leveraging this differentiation equation instead of going in the traditional methodology. For example, if x is at 5, we could see that the slope at x is 5 is 26 for this function. And if you go in the traditional method, it will be the same. So 3 into 2 is 6, 6 into 5 is 30, 30 minus 4, that is 26. So we get the same slope value by leveraging this equation instead of going in the traditional differentiation methodology. And this is done because we'll be having millions of such weights, and computing differentiation in this traditional method will not be feasible or computationally possible. And through differentiation, we can know how much of or in which direction should we change the x, like whether to increase the x or decrease the x. And in this case, in order to get the lowest loss, we need to reduce the x. And we would also know how much of x to change. So with this slope that we are getting from the differential equation, this aids us in setting up a direction and steps uh, in order to reach minima. So yeah, I think this is the crux of this lecture today, and I hope to see you tomorrow. Take care. Bye.